So this talk here is going to be a little bit about kind of like a drilled down part. It's mostly focused like for security researchers, like through the eyes of a security researcher. So while I'm like dangerous enough to kind of dig down into the proving systems and stuff like that, this is mostly going to focus like at higher levels and layers. And I'm going to go really quick, and there might be time for questions at the end, but if not, I'll provide my Telegram and Twitter and all that kind of stuff so you guys can check it out. All right, so yeah, I mentioned a little bit of this. There's kind of a few ways to think about the like cause layer for bugs in ZK. This is mostly going to be about the circuit layer, while there's also application, framework, and proof system bugs that we see. A talk about all of these would like take hours and hours. If you guys want more in-depth discussion of this, there's like an hour-long workshop from the ZK residency where we focused on this stuff. Most of the material in this PowerPoint came from that. It was like a month-long study of ZK bugs. You're also going to see me pick a lot on like the PSE ZK EVM in here. It's not because they have bad security. It's because they were right there, and I was able to be like, hey, give me all the bugs that you guys have in your repo, and I kind of picked on them and was able to pick their brains about them. All right, so this is just like a quick mention about the different bugs we see. Like, I'll mention just the stuff I'm not going to talk about, the circuit stuff, because I'll talk about that in the next slides. But the framework and proof system and application, we see all kinds of stuff, like Fiat-Shamir issues, randomness, counterfeiting. Like when I say there's like a ZK issue, that's more privacy related. We're going to focus on all this stuff right here. Another way to look at these things, this specifically with circuit bugs, is like another categorization of it is soundness, completeness, and zero knowledge. You can think of soundness as being like there's a missing constraint, so you could get something past the verifier that you wouldn't want to get past. And you can think of completeness as like it's over-constrained. So technically you could have, and these are much more rare. I don't even actually have a good example of one right now. I have something that might qualify. But this would be something like a non-malicious prover was able to make a proof that the validation circuit did not accept. So like the rollup is bricked, or the privacy system, you can't make a withdrawal, or something like that. That would be an over-constrained circuit. And zero knowledge would be like, we've broken your anonymity. So you can think of like the dusting attacks in Zcash previously and stuff like that. All right, so these are like the primary classifications of circuit bugs. This is based off of like 60 bugs that we collected and tried to kind of reason about. There's a ton of overlap. So like one bug might be like 3 of these categories. I try to basically pull a bunch of examples for this PowerPoint from the various sections. So the first one is very general. One thing I want to mention here is if you're like a traditional security person, or like you have this like Web 2 attack surface model, you can think of like client-side sanitization versus server-side sanitization. So like if you have a SQL injection vulnerability, but you put it in the JavaScript to not accept like delimiters for SQL, but then you basically allow the attacker to like go in and view source and just change the JavaScript, that would be client-side sanitization, and that's bad, right? Server-side sanitization is what we want. And the way that you can think about how this relates to circuits is that there's kind of 2 circuits. There's the prover circuit, and then there's the verifier circuit. And the prover circuit takes in the inputs and outputs like this big proof. The verifier circuit takes in the proof and outputs like a Boolean yes or no. Is it valid, or sometimes other things? But most of the time, that's how we can think about it. So in this particular case, there was an issue with the prover basically had like a constraint that said like, if you append to this tree, you append in order. So if we have these right here, we can append to just this one. But there was no check on the verifier circuit. So you could actually like append down here or here. And this was a problem because when you hash these like inputs and you basically take the transcript like that and hash it, you could basically have 2 different state updates that would like potentially brick the rollup, cause double spin, stuff like that. I won't go into too much depth on it, but you can see here with Plonky 2, the way that they fixed it is right here. And this is an actual constraint in Plonky 2. This double equals is usually a constraint in most languages. Halo 2 is a little different because you have like these different sections, but like circom, you would basically assign and constrain in the same statement, or like in the same step of developing the circuit, right? I don't want to go into too much detail on this because there's other ones I think we should focus on with the time we have. Let's see. ZK often requires modular arithmetic over a scalar field, so we have these arithmetic over and underflows. This is the most common thing that we see right now. The reason being that it really doesn't matter what type of data you have. When it's represented at the circuit layer, it's basically like a prime field that holds the input. So if you're doing like a Boolean input to a circuit, guess what? It's a whole prime field. It's not a Boolean when it's down at the circuit layer. So what does that mean? That means that we can have overflows and underflows because everything is done mod P. So if you basically subtract 1 from 0, you get P. If you plus 1 to P, you get 0. And this is not something we can just say, hey, we should alarm anytime this happens, because when you're generating randomness, which a lot of times you are for Fiat Shamir, you want this to happen, right? But if you're doing logic like multiplication, you can think of this like a traditional like integer overflow type of thing, right? For ZK EVMs, P is this massive prime number, which I'm not going to read. This is a really interesting one. So PSE, ZK EVM, SAR opcode, which is like shift arithmetic right, I think is what it stands for. It's basically just like a shift. There was an issue where shift div could basically overflow. If you go to this like GitHub link at the bottom, you can see it's linked to like where the issue's created. And this PR will show like a possible shift div that would cause this overflow. That would basically allow you to update the state. The verifier would pass it, and you could update the state to a rollup, and that would be to a rollup that's invalid. So that would be a serious problem, because then if you didn't know what happened, which it would be kind of hard to tell in some cases, you potentially like couldn't update from there because your state would be different than what you think it is when the prover is trying to update something. The fix, if you just look at the difference, it's these top 2 lines. It's basically just require equal that shift div is less than 4. Super simple, right? If shift div is 63 and you basically multiply it up here times z, it's like a whole thing, right? This is one way to think about this, and I spend a lot more time in this arithmetic underflow and overflow because like I want to drill this in, because this is the most common bug type we see by far. So this statement right here, 9 mod 5 equals 4. True. 9 plus 5 mod 5 equals 4 also. Isn't that interesting? 9 does not equal 9 plus 5. This is the root of all of these problems. This one's really bad. So Aztec had a privacy pool that works similar to Tornado Cache. And if you're not familiar, the way Tornado Cache works is you just make like a large random number, and then you can have 2 types of hashes from it. So when you deposit it, you deposit just that hash. And then whenever you're withdrawing, you basically do the second hash as your like withdrawal note, with some nuances there, and you provide a ZKP that hash was hashed from the preimage that is one of the other previous hashes. So somewhere in all of the deposits, there exists a preimage that is the same preimage for the second hash as one of those first ones, but not telling you which one, and that's how they preserve the privacy. So the problem here is that you use this as a nullifier, and so basically nobody can spin the same withdrawal twice because the hash would be the same, right? The problem here is that they bounded, they like assigned that it's more like a cast in the assignment, that the index that they used, which is part of the nullifier, was a 32-bit number. And the verifier, there was no constraint to that. So technically when you're proving, if you made a malicious prover, you could just do 32 bits plus F, right? And you would have a different hash output, but the proof to show that the preimage is one of the other ones would still pass. So it means you could have basically 32 bits worth of number of multiple nullifiers, which means a double spend. So this was like you could drain the entire privacy pool. In this case, like I showed this example earlier, the nullifier is some hash of that, and since we know that index mod p and index plus whatever mod p is the same, and there's a nuance here also, it's that the overflow actually doesn't happen. There's 2 overflows. There's technically like the integer overflow because they allowed it to be larger than 32 bits, and there's the arithmetic overflow, but the arithmetic overflow is like still valid here, right? Cool, mismatch types and lengths. Funny enough, the last one was technically a mismatch type length. This is something that plagues us always in security, especially in memory unsafe languages. You basically hand something as a byte array and somebody interprets it as a string array or some other thing, right? If somebody's expecting to have a 32-bit number and you give them a 64-bit number and there's no sanitization, there's no check, or strong typing, then you can end up with all kinds of undefined behavior, right? Which means bugs, bad bugs. I won't go through too much of this because I know that like there's no way we're gonna have enough time for it. But the issue here is that this is basically like a cast instead of like a constraint and a cast, which it should be. So the cast being the assignment. Another thing to mention here is that whenever you're working with bits, like I said, you're actually working with prime field elements. It doesn't matter if you're working with a string or bytes or what. It's prime field elements under the hood. That's how circuits work, right? Because it's a system of nonlinear equations. Let's see. This is the kind of the thing to note here. This is inside of the definition or the declaration of the particular LT chip right here. It says denotes the bytes representation of the difference between LS and RHS, so left-hand side, right-hand side. Note that the range of each byte is not checked by this config. It said it right here. The only place it was used was in another circuit where it was not constrained. It's saying we do not check this, that this is the correct type. And sure enough, somebody made a mistake. So like the question is like, how do we prevent this? This has been plaguing us since the beginning of like computer science. Like this mismatch typing and length stuff has been causing so many bugs forever. So how do we like reason about how to move forward, and maybe more on that later. Cool. This particular one, this is the shift left opcode. This is you can think of it like a cast to bytes and an equals. In CIRCOM, a double equals arrow would be an assigned and a constraint at the same time. In Halo 2, you do it a little bit different. So the issue is that there's nowhere here, even though it's like assigned and it's like, hey, saying this is a byte, there's no constraint to require it. Remember in the second circuit, the verifier. So like server-side sanitization didn't happen there, like for the analogy, right? The fix right here is to add this constraint that shift 0 is equal to basically like just the first byte of shift 0, right? Which is technically what the cast did up here. Cool, assigned but not constrained. Talked about this one already. MIMC hash is interesting. This is what caused the tornado cache double spin bug. This was actually, the fix was in the repo in a PR for 6 months. No one knew that the original like bug, the vulnerable version was on mainnet for like 6 months. Tornado cache developers found out, drained the entire pool and redeployed before any hackers got the money, thank God. But this right here, an easy fix. This is a CIRCOM quirk. If you ever see this without this little arrow, double check, because or if you see it without the second equals, this is an assignment and a constraint. So in Halo 2, this would be like both the assignment and the like CB check, right? The actual constraint added. Other nuances, and I'll talk a little bit about other CIRCOM nuances in a second, but these are just good examples of like how bad these things could be. Non-deterministic circuits. Basically, you can have more than one outcome to a given input, and this is another quirk of circuits. It's not like functional programming where you have like A equals 5. It's technically A equals 5, so 5 also equals A. So if you change something on the second half of it's a system of equations, right? It's not an actual assignment when you're talking about a circuit. So there's no input and there's no output, because you could flip the equation on the other way and it still works. So you can't think of it like traditional programming, which is I think a lot of security researchers do, and that's where they miss bugs. So the MIMC hash, the Aztec tree index I've already mentioned. There's also this Aztec-Peterson hash input. This also can allow a double spin, although it would have been tricky to pull off because it basically expands the set of possible inputs that you could give to get a valid output nullifier, right? Compiler optimization, unused public inputs. Okay, everybody's familiar with ECDSA, hopefully, or if you're not, you can check it out. But basically, you have a private and public key that you can sign something. So the public key is known, the private key is your secret. You can sign something with a private. Somebody can verify that by your public key, they're mathematically related, that it was you. This is the same thing, but in a circuit. So it's probably not as secure in a lot of ways, but you can think of it that way. So you have these inputs, you have the message, the secret key, and the private key. This circuit right here will basically return a signature that you can think of it like you're signing ECDSA. And you can see that the public inputs are the message and the public key. So the only secret input here is this private key. This right here is a problem. Well, I actually didn't include the other slide, but the original circuit didn't have the second half. And the problem was that if you were to do a signature here, you could have replay attacks because there was no m squared. This is a dummy variable. This fixes the problem, and I apologize. I should have kept the other slide to kind of show it. But what happens is that there's no nonlinear constraint. The compiler will basically not root this thing. So if I were to sign a message like, hi, I'm David, and the secret number is 5, and then give the signature, somebody else could also just take that signature and say, hey, look, the public input is, I'm David, and the message is 10, and it would actually pass. So what you do is you basically have a constraint here, which in the fiat shamir will change the randomness when you commit to the transcript, and so the signature will be like a different looking hashy type thing, right? So this is a problem. This has actually been fixed in CIRCOM. It won't let you do this anymore if you do it exactly like this. I imagine that there's corner cases where it might not be fixed, so don't trust it. Halo 2 had a similar type of thing. They have these dynamic lookup tables, and so you can have lookup tables for things like if you are going to hash a bunch of opcodes for the EVM and a ZK EVM or something like that. Why hash them each time if there's only 160? You just pre-hash them and you make a table, and then you can just look them up, and it's like a lot faster. There's not as many constraints needed. There's things like dynamic lookup tables. So in this case, you could think of like, you know, some number times something, and like just that number changes, but you don't want to some number times a hash. You pre-commute all the hashes, but you have some like multiplier or something like that. I don't know. But whenever you have this, if you don't fill in some cells, the floor planner is this like circuit optimizing like layout thing that Halo 2 will go through on a second and third pass and will like basically make your circuit as optimized as possible. If you leave these particular cells blank, then they just get completely optimized out and overwritten. And you can think of it kind of like conceptually like unsafe like memory pulverizing like in traditional like memory unsafe languages. It's not the same, but yeah. And how can we fix this? Ingtong made a cool PR here for Halo 2 that kind of fixes it by you tag like the whole column and you're like, hey, this particular column is like not to be touched by the floor planner. So I think this is something will come up again in other proof systems and other frameworks, and so something to keep in mind. This one right here, I don't want to spend a ton of time on. You can look up Frozen Heart. Frozen Heart this would be an example of a non-circuit bug. This is the framework layer. And the gist of it is like, think of the Sudoku ZK example. You give me a Sudoku and I solve it, and I don't want to tell you what the solution is, but I want to prove to you that I have the solution. You're supposed to say, okay, give me that entire row, and I just take that row of cards, because the row should have 1 through 9 in it, right, with no repeats. I shuffle it and give it to you, and then you should be happy. And then you're like, okay, give me that diagonal, or give me that particular square. And I can shuffle them, and I don't reveal the answer, but you see that like the rules of Sudoku are upheld each time, and you're relatively convinced that I know the answer. This would be like if I controlled which one you did. Like I did the Sudoku, but I was like, I'm going to prove to you I know the Sudoku. I'm going to show you the top row. And then you're like, okay, show me again. I'm like, okay, I'm going to show you the top row. And I just kept doing that. That's the problem with this particular Frozen Heart bug. The way that we do, that's an interactive proof, right? And the way that we make ZK proofs non-interactive for like validity proofs for like a rollup, for example, would be that we like basically hash the input, and then some hash we like mod it based on all the possible ways you could challenge it, and then we provide that answer, and then we hash that answer, and we keep doing that in a circle. So I show you like 10,000 solutions that satisfy all the constraints, but like I don't have control over it. And if you don't commit to the entire transcript, you get this issue where this is like entirely unsecure. You can think of this like weak randomness in the proof generation, because we use randomness to do the challenge in the like interactive challenge response version of the proof. We just make it a like one-time non-interactive proof with randomness. Cool, possible solutions. And this is where, if you guys came to TrustX, the talk ended because it was only 16 minutes. So I'll talk about a bunch of these. It looks like the formatting is nice and off because it's converted to PowerPoint, so that's fun. Cool, what is fuzzing? For y'all that aren't into fuzzing, basically you make a bunch of random inputs to functions, and and sometimes they're intelligent, and sometimes you mutate on them for coverage and whatever else, but you basically like pulverize a function to see if you can get it to crash. It's hard to fuzz a circuit, because if you want to fuzz a circuit, I'll give you an example of like 2 cases like what you would want to do. You want to find a soundness bug. Fuzzing a circuit might not help you because it's just going to basically pass true, whereas you might have like an unconstrained circuit. Finding a completeness bug would be like you fuzzed valid inputs to a circuit, to the prover, and the prover omitted like a valid proof, it's an honest prover, and the verifier said false. That is not a good proof. That would find an overconstraint there. It's harder to find underconstrained circuits with fuzzing, but it can be done with differential fuzzing, with other things. It's a little bit tricky. Not enough time in this to talk about it, but please feel free to reach out to me, and we can talk about it all we want. Specifically, the ZK EVM considerations. One fuzz test of PSE ZK EVM in March took 7 minutes, just from like start to finish. So like, just let that like for one time. And like usually like when I fuzz Go code, I'm doing like 100,000 throws per second or something crazy. So there's like a lot of like difficulties in fuzzing. So what do we want to do? Maybe we think about not fuzzing the entire PSE ZK EVM. We just get the less than gadget and just fuzz that, right? Or like that kind of thing. So there's not gonna be a one size fits all for fuzzing for sure. Oh, well, I just talked about all of these things. Didn't know I had this slide here. Compile time, runtime warnings. You can think of like if SIRCOM had said, hey, message is not constrained in like the public signature, like public private key signing signature toy example that I used earlier, that'd be like a compile time warning. That'd be great. Like an under constrained cell, assigned but not constrained, unused custom gate. Like this gate just floats. It's not assigned to anything. Like that's something we could see at compile time. So it'd be good to have these warnings. At runtime, you can think of like instrumenting. Anytime you're using an integer with multiplication, you could have something that's basically like, hey, warning, this overflowed. Did you mean it to overflow? Like just have like a same thing that you see in Clang. You get a bunch of warnings and you just say like -w, don't tell me these warnings, except like warnings that would actually be valuable for you. Specification for propagating constraint assumptions. Remember this particular one in the shift left circuit. It said this right here, but then somebody used it incorrectly. We could actually have like some sort of strong typing that would know that this thing, like the next circuit that used it, would be like, hey, this thing only is supposed to take a byte, and you're giving it, 32 bytes. Are you sure you want to do that? That kind of thing, or just not compile at all. So that would be like strong typing. Specifications for common language would allow us to do a lot of other things like symbolic execution on particular functions. And then fuzzing. You can think like a sanitizer where you, if somehow some memory region is overwritten during fuzzing, you could throw a warning like, hey, this is not supposed to be touched. Like, what the fuck? No, let's do something here, warning. Okay, symbolic execution and formal verification. Tests, and you're gonna get some really cool stuff about this later on. Formal verification is like very mathy, and it lends very well to circuits. So it's very promising for circuits. Formal verification in like traditional security, it's like, maybe it will work sometimes. You have to like basically unroll loops like 3 or 4 times. It's very inefficient, and it doesn't fit all things. It works a lot better for circuits. Obviously, the manual audits are not good enough. These are like ways for computers to satisfy things and do a bunch of math that we don't know. Challenges, it's not always applicable. It's not efficient for huge circuits. So you want to like verify the same way you don't want to fuzz the whole ZK AVM, you want to fuzz like a gadget. You kind of want to do the same thing with formal verification. Education for auditing best practices. If you guys are interested, search 0xPark ZK bug tracker online. This is where everybody's collecting a bunch of bugs. We have collected, me and some other people have collected 60 others. We're going to release some information on later this year, and we'll try to add them all there. But this has a really good, my presentation is standing on the shoulders of this giant, I'll put it that way. So check that out. Big thank you. Obviously, I mentioned that. Kyle is the one that has been maintaining that ZK bug tracker. The PSC ZK AVM team for providing a ton of examples. And then Jens, Mohammed, and Tyler were at that workshop, the QR code at the beginning of this, if you want more in-depth stuff. So they helped kind of think through all this stuff and organize this stuff. This is my InfoSecual, is my Twitter. It's also my Telegram. And then just david@ethereum.org if you have questions or you want to talk about this stuff in depth. If you want to collaborate, if you want to open source a fuzzer and have people work on it, I'm happy to connect you to other people in the industry that are working on these things. This is kind of like my night job. My day job is actually focusing on finding bugs in the EL and CL layers of the ETH L1. So I'm just kind of a noob here, but I'd like to advance my skills and happy to collaborate. Cool, yeah. How much time do we have? None? 2 minutes. I have 2 minutes for questions. Going once. Going twice. All right, in the back right.
Sorry. So, hi. I'm going to talk about this within 2 hours, but have you ever tried these new features like tags in the Circum language? I mean, there are new features that can help to avoid some of the bugs you have been talking about. So,
if they're newer than March, I know nothing about them.
No, they have kind of a year.
Okay, maybe. I do know that particular optimized out, non-linearly constrained issue is fixed. I'd be totally interested. I will totally watch your talk. I'm looking forward to it. Any others? Another one here. Let me just hand you the mic since I'm close to you.
Hi, thank you for talk. Would it make sense to run fuzzer against the Circum code, with some different execution than really proving it, to find out if there are some overflows and stuff like that?
I think you can fuzz so you kind of have to fuzz the prover. I think there's a few things you could do here. You could fuzz the actual compiler and make different test cases. You could actually compile your own things and you could fuzz the inputs to those, and that would be like fuzzing the prover, and then you could take the output and verify it, or you could just skip the verify stage. In the second case, if you're just fuzzing the prover and you're skipping the verify stage for optimization, I think the only thing that you would gain would be if you were to sanitize it in some way, mark everything that's an integer that shouldn't overflow and have it warn you if it found a test case where it did overflow or something like that. That is a good idea. One more?
And such a fuzzing of a prover can be very hard. You need to test a lot of proofs. Is it a problem?
I'd say the biggest problem is if you're fuzzing the prover, it's giving you this big gibberish output that's like the witness, and it's like you can't read it. The verifier script reads it and then gives you a 1 or a 0. So it's almost useless if you don't sanitize.